All right. So if the title gives it tells you what I'm going to be talking about, and so the why study this stuff is looking at the history of the early solar system, and some extraterrestrial samples like comets represent deep frozen bits of the early solar system that had been in cold storage in the outer system for a long time. And organics are particularly interesting in part because they may be part of the starter kit of life. And the X-ray technique I'll be talking about most, STXM, is gentler on some delicate samples like organics than GEM is. So in a chain of custody involving precious samples like sample returns, you want to do it before the TEM. And a technique I will not be talking about, but not because it's no good, but just ran out of time, is PEAM. And that's very interesting because you can see magnetic domain patterns in iron meteorites, and that in turn tells you about their thermal histories. And I'll mention that a lot of the spectroscopy that is done in the, quote, soft X-ray, quote, range is actually done by EELS, not X-ray. EELS is almost the same thing, though. And big thanks to Zach Gainforth. All the examples here will not be anything that I did. I run the beamline that some of this was done on, but it'll be all from the literature, so it's a real journal club talk. Let's see, why is it not advancing? There it goes. Okay, the technique I'll be talking about most is STXM, scanning transmission X-ray microscopy. And it's a transmission technique. You have a collimated beam of monochromated X-rays impinged on a diffractive element which acts like a lens. Some of those X-rays are focused to a near point beam, and you raster the sample through that beam in 2 dimensions, measuring the transmission as a function of position. So you get an image, something like this, where the dark areas represent more absorption. You do that repeatedly over many energies, and you get a data cube. Now the zone plate doesn't focus all the X-rays. A lot of them just go straight through or are diffracted into other orders. And to get rid of all of that stray light, you have a pinhole called the order sorting aperture, or OSA. This here is the insides of beamline, ALS beamline 5322, which had been rebuilt a couple of years ago. So the zone plate sits on the end of this brassy looking thing. Inside of that is an X-ray window separating the UHV of the beamline, which is to the left, from the system vacuum or helium. Then the zone plate can move longitudinally because the focal length of a zone plate is proportional to the energy. So you have to refocus at every energy. The OSA is hard to see, but the bracket that supports it is this. This plate here supports the sample, and this stage is a piezo stage that does fine scanning over about 60 micron range, and it's in turn carried on a coarse stage that can scan over a centimeter or so. So it's a relatively simple machine in principle, but building a good one is a bit of a trick. And the guy who built this has built several, and so he got good at it. This red light here is a laser light from the interferometer that measures the positions of everything to nanometer accuracy. Now, the utility of this can be seen if we look at carbonzanes of a number of different organic substances. And you see that they're all different and can be used for fingerprinting. And the peaks relate to different functional groups. So for instance, this peak here shows as either aromatic or C double bond C. So glucose doesn't have that because it's all aliphatic. This spectrum here I put out to the side because we'll see it again. It's graphite, and what looks like a second edge is actually an exciton. The peaks can be assigned somewhat to different functional groups. So you can look at the spectrum with these different peaks on it and make intelligent guesses as to what you have. And you can do that at nitrogen and oxygen as well. So if you think you have C double bond O, you can go to the oxygen edge and see if you get the corresponding feature. But it can be ambiguous. So if you have a peak at a particular energy, it could be one of several. So you have to know something about your system. The first class of materials we'll be looking at is interplanetary dust particles, IDPs. These are small bits of stuff that float around in the solar system and enter our atmosphere. Because they're so small and fluffy, they can, they don't get burned up. And instead they float around in the stratosphere and can be collected on plates coated with oil, silicone oil carried by spy planes. This is an image of a comet taken by Spitzer showing the trail of dust that it's left behind in its orbit. So this is the tails and this is the dust. This here is the plane of the ecliptic. So the photo has been distorted to make that a straight line, stretching from zodiacal light through zodiacal band, other zodiacal light with the Gegenschein in between. So the sun is exactly opposite this point. So it shows that that the solar system is full of dust, and some of it comes from comets. So one scientific question that could be asked is how the dust of the early solar system stuck together to form larger bodies. So if it was all just minerals, it wouldn't stick together. And there's an estimate of how strong the glue would have had to be. Well, if you look at the stuff, oh, bother. Yeah, I hope that wasn't important. Anyway, if you look at this stuff, then on the STXM, you find an organic rim around each of these particles, and that is hypothesized to be the glue. If you look at different IDPs, you find different distributions of functional groups. And even so far as one example, the authors claimed that this is evidence for the presence of C60, although the match is not exactly impressive to me. Now, I mentioned comets, and they themselves pose some interesting questions. Are they like asteroids? It was one of the first questions asked, for instance, in the Stardust program. Do they contain pre-solar material? Pre-solar material is stuff from other stars that got caught up in the solar nebula. Do comets contain stuff from the inner solar system? Comets have come from the outer solar system, but there may have been a lot of mixing in the early solar system. Yeah, so some of the types of material you can get from comets are IDPs. You collect the IDPs during transits of Earth through a comet dust stream. There's some clasts and meteorites that are believed to be from comets. Of course, with that, you have no idea what comet. And the best in terms of authenticity is actually going out to a comet and collecting some. So as a reminder, the Whipple dirty snowball model. So a comet consists, or the comet head consists of some frozen gases, or frozen volatiles, and embedded in which are solids. And you see this huge list of stuff that's in them. And this will be a theme throughout the whole talk, that all of these extraterrestrial materials contain many, many different kinds of materials. There's a lot of diversity. So one example, this was some IDPs that were collected during transit of a dust stream. And we believe that these came from that comet because the frequency of collection of IDPs increased during passage. And so in this case, they wanted to look back as far as possible to find the most primitive, as they call it, material. So these are a couple of IDPs. And doing SIMS, you find some strange isotopes. This particle here is believed to be olivine, and it's believed to be pre-solar, in this case from a red giant. This particle here has a delta D of up to 21,000 per mil, and that's not a misprint, and delta and 15N of up to 13,000. You don't get that from any solar material. That had to come from somewhere else. maybe where a little green friend came from, who knows. So you can take these these materials, if they've been put onto silicon nitride windows, you can then go ahead and do STXM on them and know where you are. And so you find various functional groups, C double bond C and so forth, including carbonate. And then you can make an extended range scan from the carbon edge around the 280 to 290 EV to the calcium edge at 350. So you can do that all in one scan. And so you got calcium, you got carbonate, so the obvious conclusion is calcium carbonate. And if you really take good data, you can see some little details around in the pre-edge, which might tell you something about what calcium carbonate it is. So these, we already saw these two grains in that this is the E1B is that pre-solar olivine that I mentioned. Now this is a long paper with a summary consisting of 9 long paragraphs and a lot of reasoning. So this is but a summary of the summary. And the blue are the sort of the most salient points, therefore a summary of a summary of a summary. So we have that 2 of these particles contain some of the most primitive materials ever seen. That we see this kind of stuff shows that pre-solar material can survive the long history of the formation and evolution of the solar system. Even organics, that the D15 anomaly, or that delta D anomaly and N15 anomaly has to be in organics. And the presence of carbonate and amphibole, those are normally found or made with liquid water, but this shows that you can get them without liquid water. Yeah, the organics and the IDP and primitive meteorites are similar, so that suggests that some of the stuff that had been in the asteroid belt made it out to the outer solar system. So there had to be large amounts of radial transport. And finally, in this section, the IDPs, collecting IDPs during enhanced comet flux would be a cheap way of getting comet material. A lot cheaper than sample return, that's for sure. But sample returns have been done. And this is just one of many, 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 many papers on Stardust. So here's an extended range scan going all the way from the carbon edge, nitrogen, oxygen. Now this is a transmission technique, which means that this absorbance is quantitative. So it really can be read in terms of column density if you do a fit to the post edge, according to the Henke tables or whatever your favorite database is. Also, getting your three XANES means that you can do the disambiguation, in that if you think you have a C double bond O on the carbon edge, you better see it on the oxygen edge as well. So looking at different points, you can then map the stoichiometry. And so the triangles are individual spots. And this circle represents an average of IDPs. And the star represents an average of Comet Halley. So what we find is that the organics are very variable. And if you've ever looked at some of the papers on say, fluorescence microprobe, hard X-ray, the inorganics are incredibly varied as well. So this would be the time for the first break.
Thanks, Matthew. It's a great start. First, just because not everyone may be aware of it, can you tell us a little bit more about the Stardust project, that being an extreme endpoint away from going up into the atmosphere and getting particles there?
Yeah, so Stardust was a spacecraft that carried with it a collector that looked kind of like a tennis racket, but between the strings are bricks of aerogel about maybe yay big. I can't tell if you can actually see my fingers.
That's good. We got it. Yeah.
Yeah. Anyway, aerogel is this very light, fluffy material that that can stop a particle moving at hypervelocity and without doing too much damage. So it went up kind of behind a comet, Comet Wild 2, and collected particles coming off the comet. and which were coming in at 6.1 kilometers per second. And so each particle would come in and then come in, hit the aerogel, and sort of crumble and leave stuff along a track. And so the heavy particle at the end was the terminal particle, and that's some minerals. And then it would leave organics and other stuff all along the track. Unfortunately, the analysis of organics was complicated somewhat because it turned out that the aerogel had some carbon in it. Oops. So anyway, the collector also had another side. It had a side which would be exposed at a time when the probe was not at a comet, but instead was passing through a stream of interstellar matter. And so this collected particles from the interstellar stream, and these are much smaller particles. They're still analyzing those. And so that's the interstellar collector. But I don't have any data on that. I don't have anything to say on that, the interstellar. But the commentary has been examined by people all over the world.
Okay.
And it was a remarkably successful mission. There was a painting commissioned of what the spacecraft would look like after it landed in the desert, and then the actual photograph looks exactly like it.
Okay. Jordi, you have a question?
Oh, yeah, I have been seeing these comments about carbinoids as carbene materials, which are formed in the extraterrestrial matter. So would you comment about it?
Carbene?
Yeah, exactly.
Okay, I haven't heard anything at all about that. That's a new one. I'd like to read about it. If you could maybe email me a reference or something.
Okay, that's great because I have seen a paper in Nature, and there have been a laser ablation synthesis here, and we are being studying this, and I have a lot of doubts about it. Thank you.
Okay, I'll definitely have a look.
There's also a question about what efforts are taken to prevent specimen contamination.
Oh, there is a lab. Well, the specimens go to, there's a lab at JSC, Johnson Space Center, and there's also right here in Berkeley at the Space Science Lab, there is a facility where they curate the stuff, and they keep it, of course, all under nitrogen. It's all in a clean room. The space probe, the sample return capsule was opened in a clean room. It was there were some witness bricks that weren't collecting anything, and those were used for contamination study. And so Andrew Westphal is the guy in charge of that, and his group developed the methods for taking out these bricks and then slicing out little tiny keystones, as he calls them. Mm-hmm. This is done using thin glass rods, which are vibrated ultrasonically to make like a micro saw. Uh-huh. It's really quite impressive technology.
Okay, very cool. How long does it take to record full spectral data for one particle?
Oh, depending on the size of the particle, the resolution that you want, that's the spatial resolution that you want. You can do a full stack in maybe an hour or a few hours.
Okay. Richard, can you unmute your mic?
Yes, I can.
Excellent.
My question is, when you block the inner part of the zone plate with a beam stop, some intensity will be distributed to the outer side lobes. Is this effect big enough that it needs to be minimized, or is it needs to be considered, or can it be ignored?
Yeah, there is a large central obstruction, just like with a telescope. Like say a Schmidt-Cassegrain telescope doesn't give you as contrasty a planetary image as say a Newtonian or a refractor. And so there is the central obstruction, and it does produce long tails on the point spread function. And so if you have, say, like little particles, and you want to get the exact composition of the little particles, let's say, for instance, we have a lot of work going on with organic photovoltaic materials, which have phase-separated morphologies. And they have to consider carefully about the point spread function. And in fact, I'm working on a paper with David Shapiro on exactly that effect, on modeling that effect and seeing what how much of an error it can cause.
Okay, interesting. Thanks.
Yeah, you can get spectral artifacts over distances considerably greater than the nominal resolution.
Okay. I'm going to suggest that you turn off your camera, Mathew. You're getting just a little bit of bandwidth limitation.
Okay, so let's see. Now all I'm seeing is my own screen. So how do I
Move the
get?
cursor to the very top.
Ah, there it is. Point.
All right, very good. You should continue.
Yeah, it's already halfway done, and I'm maybe a third done. Okay, so far we've been looking at sort of the most primitive available material. Now let's look at meteorites, which are more evolved, as they say. And this is if you haven't looked at meteorites before, they are impressively diverse. So just a very partial list of what's in meteorites, everything from metals, sulfides, oxides, down to hydrous, plus organics, which they group into soluble and insoluble, so low and high molecular weight, and even stuff that could not have been formed in the solar environment, like silicon carbide requires more carbon than was available. And back when I was running 1032, which is a fluorescence microprobe, I had a couple of hours of beam time to play with, and a section of meteorites, so I mapped it just for fun. And it gives you an idea of how diverse these things are. This red thing here is iron sulfides. The green is chromite. Everything else is various other minerals. This little blob here, this round thing here, shown in a different palette, is what's called a chondrule. And the chondrules are believed to have been formed in the early solar nebula where everything was very hot. And then the first things to condense out were refractory liquids. And then those froze. And then eventually these little round things got incorporated into larger objects like protoplanetaries and asteroids. So so these are chondrules, and any meteorite containing them is a chondrite, and that's most meteorites. To give you an idea of how diverse they are, these are the meteorite classes. And there's many of them, not just because geologists love slicing things up into many pieces and giving them all unrelated names, but also that there really are different compositions and different degrees of alteration. And why they are so diverse is that you start with the parent bodies, and depending on their size, they could be undifferentiated, as just globs of stuff that glom together under gravity, or as they get bigger, they heat up inside, and stuff melts and sinks to the heavy stuff sinks to the bottom, and you get core, mantle, crust morphology, just like planets. And then, so you're starting off with a bunch of diverse bodies, and of course all of these formed in different parts of the solar nebula with different relations to, for instance, the snow line, and then they get crunched up together, and so that crunching up process has different outcomes. So by the time you do the outer product of different parent bodies and different processing, you end up with a lot of different stuff. So one thing to ask is about the thermal history. So just like you have a doneness indicator on this roast, is there such a thing as a doneness indicator or a thermal history indicator for meteorites? And this study shows that there is, or at least in a crude sense. So here we see the XANES spectrum of organics taken from the Murchison meteorite. And then what they did is they flash heated them, and you find that the spectrum changes. And you find that it changes in a way that it looks like you're getting more of this second edge that graphite has, which is the exciton. And if you look at different meteorites, you find that they have different amounts of this. Now, we saw that exciton in graphite, but the presence of it doesn't mean that you have graphite. it's actually very hard to make graphite out of organics just by heating. Now, all you need, in fact, is just a long network of fused benzene rings. So this here is graphene, which shows it. So they then, using other estimates of temperature, correlate with the exciton intensity. So it looks like this could be a relatively simple and practical way to estimate something about the temperature history that a meteorite has gone through. Now, here, this is something that came out pretty recently, and the meteorite involved is one whose number you may recognize. It's the one that from Mars, where they thought that there might be evidence of life in it. That turned out not to be so, but it has some interesting carbonate nodules in it. And then what they did is they essentially scraped it off. They scraped off the overlying stuff, and then used FIB to really scrape it off and get a fresh surface, and then do nitrogen XANES. This is sort of not micro, it's more milli. It's spot size of 25 microns, but I'll grandfather it in. And so what you find is some nitrogen spectra that don't agree with for such things as ammonium chloride or sodium nitrate, but look more like, say, amino acids. And these are some examples of the functional groups that this would agree with. So the model that they came up with is looking at early Mars, which was a much nicer place than present Mars, if you don't mind some bombardment. You get organics formed by various abiotic processes, and these end up in the seas. Oh, come on! And and then you have the carbonates forming and trap these organics. Billions of years go by, and so this stuff has been sitting near the surface in a highly oxidizing environment. Damn it! And this shows the disadvantage of working from home. Anyway, sooner or later, my answering machine is going to pick it up. Anyways, the stuff sit on the surface, and eventually was blasted into out of Mars orbit into Earth by some other impact, and that's why we have it. So the fact that we still see these organics shows that the carbonate trapping can preserve organics over billions of years, even despite a highly hostile environment to organics. Now it's another example, aqueous alteration. It kind of, the first time I heard about it, it kind of blew my mind that there was actually liquid water trickling around in asteroids. Reminded me almost of the Little Prince. But it's apparently true, and we know that because there are things like clays on meteorites and spectrally found on asteroids. One great tool for looking at all sorts of redox processes is valence state from, for instance, L-edges. Well, most of this is done with eels, but eels is really very much like XANES. So I'll consider it to be like XANES. So anyway, what these guys did is they came up with a method for reading the valence state from the iron L-edge. So they made a lot of different minerals in the lab with known iron 2, iron 3, and then as well as some known pure phases, and then and then looked at looked at this integral over carefully chosen spectral regions. And they find if you do everything just right, you get a universal curve. And the cool thing about this universal curve is that it works for a wide variety of minerals. So it works regardless, so you don't need to calibrate for each and every kind of mineral you have. So another group applied this to an altered CAI. CAIs are calcium aluminum inclusions, very highly refractory materials from the early solar system. And so this is the CAI, and it has this aura of, or mantle of, or halo of altered material. They took a fib section here from alpha to beta, and this is the fib section. so essentially lifting it out. And so you see the, the altered CAI and then the surrounds, the matrix. So this is an elemental map, or these are elemental maps done in the TEM. And so what you see is in the matrix, you see a lot of iron nickel sulfides and calcium. And then here what you see is phyllosilicates. Now, apparently two different kinds. So comparing the elemental map from TEM, and here I stretch the color, to the STXM chemical map, what you see is that the different kinds of phyllosilicates, which have different abundances. So this stuff is iron rich, this is more aluminum rich, and this stuff that's iron rich is more iron 2 plus, and this is more iron 3 plus. Now, they go through a lot of complicated analysis and reasoning, geochemical reasoning, which I certainly don't have time to reproduce, even if I understood it all. But they came up with these conclusions. One, which you can see right off, is that iron is very enriched. There's a lot of it. And CAIs normally don't have iron. And so it must have come from other parts of the meteorite. And the obvious suspect is essentially rusting of the metals and sulfides by water. And this makes, and I imagine, they don't say it, but I imagine the sulfur helped with that. Now, since the original environment was reducing, then any iron 3 plus must be due to some other process such as water. And so, and perhaps with radiolysis and catalysis. Then their proposed mechanisms involve formations of the serpentine family mineral. They find two main populations of it. And the fact that there are these two populations with relatively sharp boundaries and not just a gradation shows that there was strong disequilibrium. Everything didn't just settle down to an equilibrium. And so they propose some complicated mechanisms that are similar in some ways to the serpentinization processes seen in terrestrial systems. So, time for a second question break.
Thank you. We'll just take a few questions here and save the rest for the end. Just because of limitations in my background, can you go back again and explain those last samples you were looking at? How do we know that those are primordial or have some idea of what their age is?
Which samples?
Let's go with the meteorites.
Okay, well, meteorites, in this case, well, I'm not sure what you mean by primordial. I mean, meteorites are bits of asteroids that have been knocked off. And so there's a whole study of meteoritics in which they look at the minerals, and that tells them things about their histories. So you look at what minerals are present, and that's why there are all these meteorite classes. So each of those has a certain characteristic minerals and distributions of minerals and elemental compositions. And so over the decades, they've come up with ways of kind of trying to figure out something about what kinds of parent bodies those came from and what processes may have occurred.
Okay.
I'm certainly not a meteoriticist myself.
All right. Matt Newville, you had a question?
Yeah, for these meteorite samples that you were talking about, there being basically a chance of weathering, was any sulfur work done on those?
Any sulfur work? You mean like sulfur XANES?
Yeah, speciation.
Not that I know of. But of course, there's been so much meteorite study, I imagine that somebody must have done it.
Right, and that would just help decide whether it was weathering or something more.
You mean like whether you see sulfate?
Yeah.
Yeah, I don't know whether they even looked for sulfate in this case.
Okay.
But yeah, I mean, the idea that it was rusting by, well, the idea that it was that the iron was distributed around by corrosion is theirs. The idea that sulfur was involved is mine, and so just a wild ass guess. That seems like if you have water and iron sulfide, I mean, it seems like a pretty corrosive mix to me.
Right. Okay. Thanks.
right, very good. You should continue, Mathew.
Okay. So here they took a piece of a very well-known meteorite and threw everything at it all at once. So you have your STXM, you have your tychography, which is a coherent imaging variation on STXM. You have tomography with energy dispersive spectroscopy and HADF. So in TEM tomography, they see on this little grain, so it's only a 1 micron grain, but they see all these different elements, which they assign to different minerals. And they also see features, which they believe to be due to thermal processing. Now, this is the Allende meteorite, which is a well-known, not very altered meteorite. So, so they think that although the parent body didn't have a lot of alteration, little bits and pieces of it did. They did tychography and STXM, and so they can get, for instance, on on the iron edge, they see the PCA shows 2 components, which look something like this. And they did the aluminum, potassium, nickel, and I think magnesium as well. Now, one of the things that they wanted to find out was the iron-nickel ratio. So you might think that you could do the same sort of thing as I showed you with Stardust of looking at edge jumps. But as you can see from these iron L edges, it's really hard to quantify the edge jump on an L edge. It really doesn't normalize very well. So they had to do some other trickery with the tychography. And tychography gives you the real part as well as the imaginary part of the refractive index. So it's the F prime as well as the F double prime. And that gives you more numbers to play with and therefore get some more information. And so they can back out with a lot of fancy math what the nickel ratio is. So PCA shows 2 components in the iron edge, which they assigned to being iron 2 plus silicate and iron sulfide. So in the sulfide, they can get composition, and they find that it matches, the blue dot is what they find, and matching to other minerals, it lines up bingo with pentlandite, iron, nickel, sulfide of this composition. In the oxides and silicate, the oxide appears to be this spinel in the chromite hercinite series, and the silicate, I believe, was a form of olivine. So the iron-nickel ratio turned out to be important. It's like where it is on this part, in identifying what the minerals are. So what they find is that all the phases seen are refractory condensates from the inner system. And although the meteorite as a whole is not highly processed, there's nanoscale bits that show that there was some shock someplace. And the multimodal microscopy gives you information you can't get just from any technique by itself. You have to do all of them. And then this is not micro by any stretch, but I couldn't resist putting it up. The transmission XANES experiment with the longest beamline ever, 6,000 light years long. Cygnus X1 is the source, and Chandra is the detector. So what they did is they stared at Cygnus X1 for a long time and collected spectral data. So this is the intensity versus energy, and this is the red line is a fit based on a mixture of metal sulfide and silicate, and they had to assume some distribution of particle sizes. And so they find a fit, and so this is, they're asking, what is the form of iron in the interstellar medium? Now, one question that's been asked for a long time is, what are gems? Gems are glass embedded with metals and sulfides. They're little tiny particles found in meteorites and comets, and they're somewhat mysterious. And one question is the silicate component gems? And it turns out that you can't make that work with all the constraints. This red fit doesn't look that much worse than this red fit, but if you look at the chi-square, it turns out to be, it is significantly worse. Now, an interesting feature, so here's the iron L edges. An interesting feature is this little uptick. And you might ask, why would a transmission spectrum show an uptick? And the reason is that in this experiment, you're not looking at absorption, you're looking at extinction. The solid angle here is tiny, like maybe microradians. I don't have a good estimate for the source size. So that means that any scattering will will put the X-rays out of the field of view and therefore look like absorption. And scattering depends on the real and imaginary part, therefore an F prime and F double prime, and F prime has this pre-edge dispersion feature. And that's why it looks like that. So we get information about the interstellar medium. Whoops. So summarizing, these materials are very, very heterogeneous on scales onto nanometers. So you really need microscopic methods. You need the chemical sensitivity. The XANES-based methods are useful for identifying the functional groups and the oxidation states. You usually have to do other techniques, STEM, Raman, infrared, on and on and on and on. And I apologize to the PEAM people that I just ran out of time on making it, and in terms of getting that stuff in. But I can ask what I could, if I could describe that work a bit if anyone wants. And that's it.
Thank you. That was really interesting. To begin the questions, Tim Hyde, can you unmute your mic?
Hi, Mathew. Very interesting talk. Being somebody who's not an expert in STXM, just interested in, clearly you're not dealing with much material ever. So what's the sort of smallest size of feature particle that you actually can analyze using the technique?
Well, the spot size is more or less is typically around the size of the outer zone of the zone plate. So typically around 30 nanometers. The resolution on tychography, which is a kind of a STXM relative, can be down in the few nanometers. So in principle, if you had, for instance, a dispersion of particles that were tens of nanometers, then you could analyze them at least somewhat. You wouldn't be able to spatially resolve them, but you get some spectroscopy out of them.
Okay. Yep.
Very good.
Nanometers. Yep.
What do we?
I should mention that for carbon edge, the thickness that you need is sort of like 100 nanometers, is about the maximum. Say a couple hundred nanometers is about as thick as you can use, and then that goes up as you go up in energy. So the rule of thumb is that if a sample is usable for TEM, it's usable for STXM.
Okay.
Sure.
Okay. Looking to the future, what projects do you know of on this business of getting extraterrestrial materials where people are going to be looking for synchrotron use?
Okay, well, of course, the Japanese have their asteroid sample return mission. Yeah, Hayabusa and new ones, and there's other new ones coming up. So when that stuff comes home, then there'll be a mad rush for synchrotron time.
Got it. The fourth generation synchrotrons, what's their impact as regards to the practice of STXM?
Okay, for STXM itself, maybe not as much. Well, it depends on whether you're on a bending magnet or an undulator. STXM is kind of a brightness limited experiment. So you could get a lot more flux. You won't get more resolution out of the STXM, but you'll get more flux. This may or may not be all that useful because of damage. However, tychography it will definitely be upgraded because as of now it can be brightness limited, and so you'll be able to do things a lot faster. You'll be able to do tomography and so forth, and so you'll be getting torrents of data. At ALS, we're going to have this upgrade to ALSU in a few years, and our tychography microscope is definitely in line to be put on a new beamline. We're also going to have a tender X-ray tychograph, so that'll go up to 8 kilovolts.
I see. That'll be really interesting. The people who have these materials, what's the one thing they wish they could do that presently we can't give them at the synchrotrons?
That's a good question. I can't really, I don't really know. I think mostly just being able to do more of it, because these materials being so diverse, you really have to study a lot of different samples and a lot of different regions on a sample. So so I think you really want to be able to study many particles many times. Some of the aerosol, the people who work on aerosols have solved some of that with some automated analysis. So there are papers where they show hundreds and hundreds of particles. And so something, I would guess that, haven't talked to the meteorite and comet people much about it, but I would guess that the automated analysis and sample transfer will be very important.
Okay, very good. Thank you again, Mathew. That was a fascinating
and maybe cryo as well to slow down damage.
Ah, that makes sense. Okay.
Unfortunately, it doesn't get rid of damage, just slows it a bit sometimes.